Welcome. So in the last lecture, we have discussed about FCFS, first come first serve scheduling algorithm. So in this lecture, we'll be discussing about shortest job first scheduling algorithm. Okay, so the drawback with the FCFS algorithm is that it has a very high average waiting time. So to overcome that particular drawback, this algorithm, what it does in the sense, in the ready queue, from the ready queue, say at a given time, ready queue contains n number of process. Then from that, it will pick up the job which has the shortest time of CPU burst, and that job will be first, it will be executed by the processor. Once that job completes, again again the operating system will check the ready queue, which process is having the shortest CPU time. So again, that whichever the process currently is having the shortest CPU time, that will be allocated to the CPU, and the processor will execute that particular job. Okay, so this is how shortest job first scheduling algorithm works, and and it provides an optimal average waiting time, and it provides an optimal average waiting time. Okay, so shortest job first scheduling can be implemented in two ways. It can be implemented either as a preemptive scheduling or as a non-preemptive scheduling. So you can do it either way. So it is not that it should be done only in the preemptive fashion or in the non-preemptive fashion. So it can follow either preemptive scheduling or it can follow non-preemptive scheduling. Okay. So first we will discuss an example uh, under non-preemptive scheduling of shortest job first. So in non-preemptive scheduling, how it works in the sense, it will from the ready queue, it will pick up, the operating system will pick up the job with the shortest duration of CPU burst, and that will be given to the CPU, and the CPU will execute that job, and once that particular job terminates, again from the ready queue, whichever the job which has the shortest CPU burst, that job will be picked and that will be given to the CPU, and again that job will execute and it will terminate. So this process continues until there are no jobs or no process in the ready queue. Okay, so this is how the shortest job first works in non-preemptive way. Okay, so let us go through the algorithm with an example. Okay, so basically, every CPU, every process will have a CPU burst. So this algorithm will pick up the job with the shortest CPU burst, and that will be given to the CPU. Okay, so it gives the minimal average waiting time. So it gives an optimal performance. Okay, but there is a drawback with the shortest job scheduling, and that drawback is how will you find the next CPU burst? So generally, the operating system cannot know the next CPU burst. That is how much time the next time when the uh, when the turn should be given to a particular process. Okay, because CPU keep on context switching. So when the next when next a particular process will be given to the CPU, how much time this process will take? Will it take 3 milliseconds or 4 milliseconds or 10 milliseconds, or that time is not actually known already. So that depends on the behavior of the process. So this is actually one of the crucial question: how much time that particular process mm, will take. Okay, that we don't know. So how to deal with that issue, that we'll be discussing later. Okay, in this lecture itself we'll be discussing, but not right now. Okay, so so this problem is with respect to both preemptive and non-preemptive scheduling, because in shortest job first, you want to know the CPU burst. Only based on CPU burst, you are going to pick up the job, whichever the job has the the shortest CPU burst, shortest remaining CPU burst. That for that particular process, you are going to give the CPU. The operating system is going to give the CPU. So how much burst time remains? Generally, we don't know that. Generally, the operating system don't know that. So, so there is a difficulty in that. So how to overcome that difficulty? That also will be discussing. So one of the option is you can ask the user. You can ask the user itself when the user is submitting the job. You can ask the user how much time this, how much CPU time this particular job may take. Then the user should have the knowledge to say that probably it may take 20 milliseconds or 30 milliseconds. But if the user is not having that knowledge, then it may not be appropriate. Okay. Fine. So let us understand how this algorithm works in a non-preemptive uh, style. Okay. So let us assume these are the process currently available in the system: P1, P2, P3, and P4, and these are the burst time. P1 needs 6 milliseconds, P2 needs 8 milliseconds, P3 needs 7 milliseconds, P4 needs 3 milliseconds. And the algorithm shortest job first, what it says, it will first execute the job with the shortest burst time, CPU burst time. Then the next, then next. Okay. So here the shortest burst time is for process P1. So process P4. P4 is having 3 milliseconds. So first it will execute P4. Then the next shortest is P1. So next it will execute P1. Then the next shortest is P3. Then it will execute P3, and the next shortest is P2. Then it executes P2. Okay, this is the order it will follow. First it will execute the process P4, then the process P1, then the process P3, and at last the process P2. So the Gantt chart, how it will look like. So if you draw the Gantt chart for this particular case, so at first process P4 will execute, and process P4 will start at 0th millisecond, and it will end at, it needs 3 milliseconds. So it will end just at the beginning of the 3rd millisecond. Okay. And then which process will get the CPU? P1 will get this, P1 will get the CPU, and P1 will execute for 6 milliseconds. That is, it starts at 3 millisecond and it will execute up to 9th millisecond. Okay. Next, once P1 completes, then P3 will get the CPU. Okay. And P3 needs 7 milliseconds. So it starts at 9th millisecond and it ends at 16th millisecond. And then P4 will get the process and it needs 4 milliseconds, it needs 8 milliseconds. So it starts at 16th millisecond and it ends at 24th millisecond. Okay. So this is how things works here. Okay. So now we can see the waiting time. So what is the waiting time for P1? P1. So here we are assuming all jobs arrive at the same time, T naught, but this is the order in which it is getting executed because of the algorithm. Shortest job, first algorithm, it always picks the job with the shortest remaining time. Okay, shortest duration. Okay, so P1 waiting time is 3 millisecond. Waiting time for P1 is 3 millisecond. So waiting time for P1 is 3 millisecond, and the waiting time for process 2, sorry, this is the last one, is process 2. Okay, this is process 2. The waiting time for process 2 is 16 millisecond. The waiting time for process 2 is 16 millisecond. Okay, and the waiting time for process 3 is Waiting time for process 3 is 9 millisecond. Process 3 starts at 9th millisecond. And the waiting time for process 4, the waiting time for process 4 is 0 millisecond. Okay, that is process 4 is not at all waiting. Okay, it comes and it got the CPU. Okay. So P4 is the one which gets the CPU first, and then P1, and then P3, and then P2. So this is the waiting time. So now if you calculate the average waiting time, it is 3 plus 16 plus 9 plus 0, okay, by 4, whatever the value you are getting. Okay, so 16 plus 3 19, 19 plus 9 28, so it is 28 by 4, so 28 by 4, which is nothing but 7. So the average waiting time here it is 7 milliseconds. Okay, so always the shortest job first, it gives the shortest, it gives the minimum average waiting time. So that is the advantage of this algorithm, right? So that is the main advantage of this algorithm. And the disadvantage of this algorithm is, but how the operating system will know the next CPU burst of a particular process. So that is the challenge with respect to this algorithm to implement it. So for implementing, there is a challenge, that is to identify the next CPU burst. So this is the scheduling chart or the Gantt chart. So it executes in this order: P4, P1, P3, and P2. P4 executes for 3 milliseconds, then P1 for 6 milliseconds, then P3 for 7 milliseconds, then P2 for 8 milliseconds. So the average waiting time is this. So P1 waiting time is 3, P2 waiting time is 6. Okay, P2 waiting time is the waiting time for P2 is 16, and the waiting time for P3 is 9, and the waiting time for P4 is 0. So the average waiting time is 7 milliseconds. Okay, fine. So before this, let me discuss something else. So now let us discuss. So whatever we have discussed in the previous case, which is an example for a non-preemptive scheduling for shortest job first algorithm. Okay. Now let us discuss shortest job first algorithm in using preemptive scheduling. Now let us discuss shortest job first algorithm using preemptive scheduling. So if shortest job algorithm uses preemptive scheduling technique, then it is called as shortest remaining time first algorithm. Okay, then it is called as shortest remaining time first algorithm. Okay, so generally the algorithm is called as SJF, shortest job first. If it is using non-preemptive scheduling, it is just called as shortest job first algorithm. But if it is using preemptive scheduling, then it is called as shortest remaining time first algorithm. So you know what is preemptive scheduling? That is, the CPU can be taken away from the process at any time if the operating system wants to do so. So let us discuss this scenario with an example. Okay, here we add the arrival time also to the input. Okay, so these are the process. So currently we have these process P1, P2, P3, P4. But if you see, the arrival time of each of these processes are different. P1 arrives at 0th time, P1, P2 arrives at time slot 1, P3 at time slot 2, and P4 at time slot 3. And these are the burst time. P1 needs 8 milliseconds, P2 needs 4 milliseconds, P3 needs 9 milliseconds, and P4 needs 5 milliseconds. Now how the Gantt chart will look like for this particular scenario. So let us uh, assume time 0. At time 0, which process is there? Only P1 is there. There is no other process. P2 comes at only first millisecond. P3 comes second millisecond. P3 comes third time slot, milliseconds or time slot. So at time 0, there is only one process. So you have to consider only this because there is nothing to compare. Okay. So the CPU will be given to the process P1. But P1 will execute for how much time? In the sense, it will execute only up to time slot 1, because at time slot 1 you got another process with a shorter duration. At time slot 1, there is another process P2. And what is the duration of P2? P2's burst duration or burst time is only 4 milliseconds. Okay, so at time 1, P1's remaining time is how much? 7. But there is another job at time 1, that is P2. P2's remaining time is 4. So the shortest remaining time first algorithm picks the one which has the shortest remaining time. So the remaining shortest remaining time is for the process P2. So P2 will execute. Okay, P2 will execute. It will continue execute. At time slot 2, P3 comes. At time slot 2, P3 comes, but it needs 9 milliseconds. It needs 9 milliseconds, and by that time, already P2 has completed 1 millisecond. That is, its remaining time. It needs only 3 milliseconds. So again, this is the shortest remaining time. So P2 will continue. So P2 will continue. At time 4, at time 3, P4 comes, and it needs 5 milliseconds. By the time P4 has finished one more slot, one more time slot, so it needs only 2 more milliseconds. So again, this is the smallest job. So this will continue. So P2 will continue for next 4 milliseconds continuously, and it will finish its work. At 5th millisecond, P2 will complete. Okay, at 5th millisecond, P2 will complete. So now 5 milliseconds over. Now P2 has already finished the task. Whatever P2, the particular process P2 has already completed. So we can cut off P2, that is P2 has finished, and P1 has a remaining time of 7 milliseconds, and P3 has a remaining time of 9, and P4 has a remaining time of 5 milliseconds. So which job will get the process? Which job will get the CPU? P4 will get the CPU. So P4 will execute for another 5 millisecond. P4 will execute for another 5 millisecond. That is, it will complete at 10th millisecond. Okay. So now P4 is completed. P4 is completed. Now there are only two jobs, P1 and P3. So the shortest duration is there for the job P1. So P1 will get the CPU, and P1 will execute for next 7 milliseconds. That is, it will execute up to 17th millisecond. Okay. So now P1 is completed. So the remaining only job is P3. So finally P3 will get the processor, and it will execute for the next 9 milliseconds, and it will complete at 26th millisecond. Okay. So here the average waiting time, if you see for P1, if you see the average waiting time, at first the moment it enters, it got the CPU, and it already executed for 1 millisecond. It already executed for 1 millisecond, but then it has to wait up to 10th millisecond. So this 10 minus 1, this is its waiting time. So 10 minus 1, which is 9. So the waiting time for P1 is 9 millisecond. Okay. P1 should wait for 9 milliseconds. Okay. Waiting time for P2. So waiting time generally you can calculate as starting time minus arrival time. Okay. Starting time minus arrival time minus previous burst, if there is any previous burst. In case of P1, there is a previous burst. You can say the starting time was 10. 10 minus arrival time 0. 10 minus 0 is 0, but already it has completed one burst. So that is 9. So for all other process, it is just starting time minus arrival time. So P2 it started at first millisecond. Its arrival time is also first millisecond. So 1 minus 1 is 0. Okay. So the waiting time for P2 is 0. There is no waiting time. And the waiting time for P3 is, it started at 17th millisecond, and its arrival is 2 millisecond. Second millisecond it arrived. So 17 minus 2, its waiting time is 15 milliseconds. Okay. That is for P3. Okay. And for P4 started at 5th millisecond. P4 started at 5th millisecond, and its arrival time is 3rd millisecond. So it is arrival time minus starting time 5 minus 3, it is 2 millisecond. Okay, so the waiting time for P4 is 2 millisecond. Okay, so now the average waiting time can be calculated by adding all these things and dividing by 4. Okay, so that is 9 plus 0 plus 15 plus 2 and divided by 4. Okay, so which is how much? 15 plus 9, 24, 24 plus 2, 26. Okay, 26 by 4. Okay, okay, so it is 6 point something, right? Right, okay, 6.5 or something, right? Okay, so this is how uh, we calculate uh, the shortest, I mean, the average waiting time for shortest remaining time first algorithm. Shortest remaining time first is nothing but a shortest job algorithm which follows preemptive scheduling. Yeah, so, so basically, so the Gantt chart, it looks like this, whatever we have discussed so far, and this is how the average waiting time is calculated. It comes to 16.5. Okay, so this is how things works in the shortest job first algorithm. Okay, now coming to that point, so we have discussed that there is a drawback with the shortest job first algorithm. What's the drawback? The drawback is it the operating system don't know what will be the next CPU burst for a given process. So in that scenario, what can be done? In that scenario, what can be done in the sense we can use an algorithm called as exponential averaging. You can use an algorithm called as exponential averaging, and using this algorithm, we can predict the next CPU burst for a given process. We can predict the next CPU burst for a given process. Okay, so let us consider this graph. So this graph actually, it talks about a particular process. So this particular graph, it is about a given process. Okay, so let us say this process can be anything. Say maybe this is a word application, or it may be a notepad, or it may be a gaming application. Okay, so so this in this graph, this t is t. Okay, this t is this particular thing. So this thing shows uh, the previously how this particular process was being used. Okay, that is previously how this particular process behaved. That is during each time, uh, what is the CPU burst it used. Okay, so this is the behavior of this process previously when it was used. Okay, that is during time slot 0. During time slot 0, it used CPU for 6 milliseconds, and during time slot 1 it used CPU for 4 milliseconds. During time slot 2, again it used CPU for 6 milliseconds. Again, during time slot 4, it used for 4 milliseconds. During time slot 5, 13 milliseconds. Again, 13 milliseconds. Okay. So this is how this particular process behaved previously. During each time slot, how much CPU burst it used. Okay. How much time it uses the CPU. During time slot 1, 6 millisecond, time slot 2, 4 millisecond, 3, 6 millisecond, 4, 4 milliseconds, so on and so forth. It proceeds. Now, say, say this is how this particular process behaved yesterday. Let us assume yesterday when you opened this process, it behaved in this way. Now today also you are opening the same process. So is there any way to predict like how it will behave today? You may not be predicting accurately, but at least if you come close, it will help us to implement the shortest job first algorithm. Okay, so can it be done? So yes, you can do that. You can do that using an algorithm, and that algorithm is called as exponential averaging. Okay, So this exponential averaging is given by this formula. So what's the formula? Tau of n, tau of n is equal to alpha Tn plus 1 minus alpha into tau n. Okay. Tau of, see, this is tau of n plus 1. Okay, sorry. This is tau of n plus 1. Tau of n plus 1 is given as alpha Tn plus 1 minus alpha into tau n. Okay. Tau of n plus 1 is given as alpha Tn plus 1 minus alpha into tau n. So what is here uh, tau t, all these things. So t is, Tn represents what is the CPU burst demanded by this process previously. When you execute previously, how much CPU burst it demanded during during each time slot. That is what Tn. Okay. So here you can say that T naught is 6. When it is executed for the last time, T naught value is, it used CPU for 6 milliseconds. T1 is 4. That is, when this process is executed previously, it used CPU for 4 milliseconds. T2 is 6. Previously, when this process was executed, during third time slot, okay, or during 0, we started with 0, or during the second time slot, it uses 6 millisecond. And during third time slot, it uses 4 milliseconds. So this is nothing but T naught, okay, and this is T1, okay, and this is T2, and it proceeds. Okay, so that, so this is basically Ti. Okay, so that is what T naught in that particular, Tn in that particular equation. Tn is when that particular process executed previously during nth time slot, what is the CPU burst duration. Okay, right, and tau n is what when this uh, tau n is the tau n plus 1 is the prediction. Tau n plus 1 is the prediction for the next time slot. Tau n plus 1 is the prediction for the next time slot. Okay, tau n is the prediction for the previous time slot. What is the value predicted for the previous time slot? That is tau n. Okay, so if you go back here, this is what tau 0, this is tau 0. So this is tau 1. Okay, so to identify tau 1, we need two things. We need tau naught, and also we need T naught. Okay, so that is what in that equation. So tau n is the predicted value in the previous time slot. Tau n plus 1 is the predicted value in the next time slot. Okay, and alpha is a parameter. Let us come to the alpha little later. Alpha is a parameter which is used, and generally alpha holds the value 0.5. Okay, generally alpha holds the value 0.5. So this is how this particular equation is defined. So here mm, what are the things? Tn is the actual length of the nth CPU burst. Okay, so nth CPU burst, how much time it occurs, and tau n plus 1 is the predicted value for the next CPU burst. Okay, tau n is the, what is the predicted value for the previous CPU burst, and alpha generally ranges from 0 to 1, but normally we pick the value as 0.5 for alpha. Okay, normally we take the value as 0.5. Okay, now why should we take 0.5? Some justification we should give. It can go from 0 to 1. Why should we take only 0.5? So if you take alpha as 0, then what happens in the sense, if you put 0 to this equation, what happens? Then tau n plus 1, will be, sorry, tau n plus 1, yeah. So just put 0 to this equation for alpha and calculate what is tau n plus 1. So if you apply 0, this term will become 0. Okay, and 1 into tau n, you will get tau n, and minus alpha tau n also will become 0. So if you keep alpha as 0, then tau n plus 1 will be equal to tau n. Tau n plus 1 is what? What is the predicted value for the next CPU burst? Tau n is the predicted value for the previous CPU burst. So then the next CPU burst will only depend on the previous CPU burst. So there is no history will be ignored. I mean previously, history in the sense previously how this particular process behaved, that will be totally ignored uh, if you consider alpha as 0. Okay, if you consider alpha as 1, then what will happen? If you consider alpha as 1, in that scenario, what will happen? Just apply alpha equal to 1 in this particular equation. So if you apply alpha as 1, then how this particular algorithm will behave. So if alpha is 1, then tau n plus 1, okay. So tau n plus 1 will be equal to, so the first term will be Tn. First term will be Tn. And what will happen to the second time? You are applying alpha as 1. So this 1 minus 1 will become 0 and this entire second term will become 0. So tau n plus 1 will be equal to Tn. So it means it only depends on the behavior of the previous execution of this particular process. That is tau n plus 1, it only tau n plus 1 is the predicted value for the next CPU burst. Tn is the previously when the process executed, how much time it took for the nth time slot. It only depends on that. No history is involved. Okay, that is the reason we are setting alpha as 0.5, so that when you keep alpha as 0.5, it will use it will use the current prediction, and also it will use the previous history. Okay, so the learning will happen based on the current prediction, or the prediction will happen based on the recent prediction, the previous predicted time previous predicted time duration plus the history. Both will be utilized when you assign alpha as 0.5. That is the reason we are using alpha as 0.5. So this is the reason why alpha is given a value 0.5 here. Okay, so that's what I just wanted to say. So this is how we can predict in case of SJF. So why we are doing all these things? Because in SJF you don't know what is the next CPU burst of a particular process, and it depends on that. So commonly alpha is set as 0.5. So preemptive version of SJF is called as shortest remaining time first. So this slide shows what will happen if alpha is 0 and what will happen if alpha is 1. Okay, if alpha is 0, the recent history will not be counted. If alpha is 1, only the actual past CPU burst counts. So we don't want both to happen, we want both to be included. Okay, so we keep alpha as 0.5. Okay, now let us go back here. Okay, so now, so initially, so now you know what is T naught. You know what is T naught. But there is sorry, you know what is alpha, but there is another thing we need. Tau naught we need to start, because initially there should be some tau value. Okay, so this tau naught, how it is calculated, in the sense it is a constant. Tau naught is a constant. So what you can do is, previously how this algorithm behaved, you know. So those values, whatever you have, you can take an average of that and you can keep it here. Okay, so if you take the average, it may not be exactly 10, but something close to the average. Okay, so I think it comes around 8 point something. So you can even keep 9 also, that's not a problem, but here it is assumed as 10. So now you have the value tau naught. Okay, so tau naught is 10. So now you want to predict in the next slot how much cycle this particular so what will be the CPU burst duration of this particular process. So just you can fit into this algorithm, I mean to this logic. What it says, tau n plus 1 is equal to alpha Tn plus 1 minus alpha into Tn. So here what is Tn? So Tn is 6, that is This is the first slot. Okay, this is zeroth. So T1 is 6. Okay, T1 is 6, and you know alpha is 0.5, so it is 0.5 into 6. Okay, 0.5 into 6 plus 1 minus alpha, that we know, 1 alpha is 0.5, so 1 minus alpha is 0.5 into tau n. What is tau n? So we are calculating tau 1. So tau 1 is we are calculating. So so tau n is nothing but tau 0. So tau 0 value, just we assumed it is 10. Okay, so it is into 10. Okay, so what you get is, actually it is 0.5 into 6, which is 3, and 0.5 into 10, which is 5. So 5 plus 3 is what? It is 8, and that's the value there. You are getting the value, uh, 8 you are getting here. Okay, so basically it is 0.5 of this should be multiplied with 0.5, and this should be multiplied with 0.5, and add this two. Similarly, next value, you multiply this with 0.5. 4 into 0.5 is 2, and 8 into 0.5 is 4. So 4 plus 2 is 6. That is why we got this. Similarly, this value, 6 into 0.5 is 3, and 6 into 0.5 is 3. So 3 plus 3 is 6. Similarly here, 4 into 0.5 is 2, 6 into 0.5 is 3, 3 plus 2 5. Then this 13 into 0.5 is 6.5. Okay, 6.5, and 5 into 0.5 is 2.5. Okay, so which is nothing but 9. Okay, so like that it proceeds. Okay, so now if you draw this as a graph, if you plot this, what you will get is nothing but what is the other graph that is drawn. So this is what you are getting. Okay, so I mean, it is somewhat behaving in the similar fashion, so you can almost predict how it behaves. Okay, so this is how we can implement the shortest job first algorithm. Okay, right? So to summarize, shortest job first algorithm always takes the shortest job, and it executes. It can be implemented in either way, either in a non-preemptive style or in a preemptive schedule, and it gives the best performance in terms of average waiting time. It gives the minimum average waiting time. But the drawback with the algorithm is that operating system generally don't know how much CPU burst will be required by the process. So for calculating that, we are using the exponential average. Okay, fine. Thank you.